Welcome back to Computer Science 4303. Today, we are going to be talking about grid algorithms. What I mean by grid algorithms, we talked about space representations and grids in the last lecture. And so grid algorithms are going to be algorithms that you can run on these grids that are sort of time and memory efficient and specific to grid data structures. And so we'll see why that may be important going forward for assignment 2. And just remember that after this lecture has finished, quiz 3 will be available, and that is going to be related to this lecture and the previous lecture from Tuesday. All right, so let's get started with the lecture. So, grid algorithms. We're going to be talking again about algorithms that can be run on grids, specifically in this case for pathfinding. And then at the end of the lecture, we're going to drill down specifically into vector fields and influence maps, because assignment 2 is going to be all about influencing vector field pathfinding for grids in games. So, grid algorithms. We're going to talk about connected states. So one of the prerequisites for this course is COMP4303, and we're going to be revisiting the most notorious assignment from that course, which is assignment 2, in order to recap our knowledge of like breadth first search and connected states, because I think it's an important concept and we could use a little refresher on that. Then we're going to be talking about something called a distance map, and that'll allow us to compute a data structure which allows a constant time lookup for ground distance for multi-agent single goal planning. And third, we'll be talking about a vector field, which we're going to construct from the distance map. And that's going to allow us not only to get the distance, but to get the direction of travel that we should have from any point on a map to a single goal. All right. So first, let's talk about connected states on a map again. So states, or in this case of grid algorithms, a state is essentially a cell in the grid. States are connected in a grid if a legal path exists between them, no matter how long, okay? And so if you remember, we're going to choose 2 points on the map, and if a path exists between them, then those we're calling connected, all right? So you can move from one of them to the other one, so that's what we're defining as connectedness. A connected sector, this is a term that I came up with, is the entire set of states that are all connected to each other. Okay, so if 2 cells are connected, then they belong to the same connected sector. And everything within a connected sector is connected to everything else within that connected sector. And just as a quick reminder, connectivity is transitive, right? So it has a transitive property, which means that if A is connected to B and B is connected to C, then that means, well, A can go to B and B can go to C, so therefore A can go to C, and so A is also connected to C. All right. So what are we talking about when we talk about connected sectors? So let's look at this, this sort of environment that we had in 3200 and see what we mean by that. So in this environment, you can only pathfind entirely within cells of the same color. Okay, so that's what we're defining these colors to mean. Doesn't necessarily mean one is water and one is grass or stone or whatever. It's just a coloring system. But you can only walk between cells of the same color. And in this case, we're only doing up, down, left, and right movement. So that means, in this case, that these 2 cells, or these 2 states, are connected, okay? Because a path exists from one of them to the other one. So you can see up here in the top left, we have this state, and we can travel to this state down here. So these are connected states. These 3 states on the map, A, B, and C, well, let's just see if those are connected. Well, we can travel from A to C, right? And we can travel from A to B. Therefore, we can travel from B to C, and so all of these states are connected, okay? So if you can travel between them, they are connected. These states, however, are not connected. And why aren't they connected? It's because in this environment, you can only pathfind between nodes of the same, or states of the same color. Okay, so this one, if you try to get to this one, you're going to run in from blue to green, and that's an illegal action in this state. So those are considered not connected, right? So therefore, using that definition, this pink area here is a connected sector. meaning that every cell within this pink area is connected to every other cell within that pink area. Okay, so I've got a red cursor here, apologies, but like this one up in the top left is connected to this one in the bottom right and also connected to this one. Any of the pink ones are connected to any of the pink ones. Okay, and it turns out that this whole green region is connected, this whole green region is connected, this whole gray region is connected, and the whole blue region is connected. Okay, so just keep in mind that just because this region is green and this region is green doesn't mean that these two regions are connected. They are each their own connected sector. Okay, so how would we compute connectivity? And this I know is a recap from a previous course, but it turns out that this connectivity computation, that's a tongue twister, is going to be really related to the computation of vector fields. And so we're going to review something that we already know in order to get something that we don't know, okay? So, two states are connected on a grid if any four-directional path exists between them. And so what we can do is we can use a breadth-first search to determine four-directional reachability. So instead of computing separate paths, we can instead compute them all in one pass, okay? And we'll see what that means when I show an example later in the lecture. And so the complexity of this breadth-first search is going to be equal to the number of states or cells in the grid, okay? So let's just recall our algorithm for breadth-first search. Even though it's kind of a simple algorithm, we still want to look at it. So this was our, in 3200, we had general uninformed tree search, right? And this tree search could be easily changed into breadth-first search by just modifying the open list into a queue. Remember that? So breadth-first search essentially just has what we call the open list as a queue. It starts with the node which contains the initial state. And then while true, if we have an empty open list, it means we haven't found any solutions, okay? If we don't have an empty open list, then we pop the node off of the queue. If that node state is the goal, then we've reached our solution. Otherwise, we push that node, or push the expanded node. Sorry, we expand the node generating its children and push that onto the open list, okay? So that's the simple breadth-first search algorithm. We covered that in great detail in 3200. Here is a visual example of breadth-first search. So if we were doing breadth-first search for single agent, single goal pathfinding, let's say we wanted to go from A to C in our map, right? So what we would do is we would start looking at the children of A. So the open list is not empty. So we generate the first child, we add it to the open list, we generate the next child, we add it to the open list. So we're going in a breadth-first manner. So then from D, we're going to check all the children of D, right? So that would be A, B, and E. So we check all of those children. And then from B, we would check C, E, and A, and D. And so this is a breadth-first search algorithm, right? We go, the reason it's called breadth-first search is because we go one action at a time, and we search all of the neighbors of a child before we go down deeper into a tree. Okay, so that's all just a little bit of a recap of BFS. So what does breadth-first search look like in a grid? If we don't remember, well, we're going to start at a particular node, or a particular state, sorry, and then we're going to search outward in four directions, eventually covering the entire map, right? So that's what breadth-first search is going to look like. All right, so the performance, as a recap of breadth-first search is a complete algorithm. Complete meaning it explores the entire tree. And so it will find a goal node if a goal node exists. Oh, excuse me 1 second. I got a visitor here. Just want to show you. He's so strong, he just opened the door to my office. We have sliding doors. Hey, Freckles, say hello. Say hello. He wants to go outside, so he just jumped out of my arms. Give me 1 second. I'm gonna let him outside. Yeah, he's an outdoor cat. He doesn't like being indoors. He comes inside to eat our food and sleep in our bed and then leave again. So just give me 30 seconds. I'll be right back. So Freckles was let outside. The crisis was averted. So back to the BFS performance. This is what you get working from home, right? Yeah, I know, he's super cute. And now he's super cute, but now he goes outside and like murders all the birds and squirrels and stuff in the area, so he's not that cute. All right. So BFS is complete. What does complete mean again? It means that it explores the entire tree, right? So if a goal exists, if a path to a goal exists, it will find that goal node. But BFS will find the shallowest goal node, since it explores all nodes at a given depth before exploring the next depth, right? So let's go back to our example and look at that. So here, when we did BFS in this graph structure, BFS found node C, but it found the shallowest path, not the optimal path, right? So BFS doesn't take path costs into account. So you can see here, the path cost from A, B, C is 11. But if we had gone A to D, D to E, E to C, that path cost is 7. And usually we want the lowest path cost, right? So we hadn't explored any paths of length 3 yet. We have just explored all paths of length 2. And so just remember that when it comes to that, BFS is not optimal, okay? So BFS in general is not optimal. It does not produce optimal solutions, since the shallowest node is not necessarily the optimal node. So BFS is optimal if the path cost is non-decreasing as a function of depth. Usually what that means is that BFS is optimal if all action costs are the same. Okay, so if all your action costs are equal, then you have a shallowest solution having an equal, all the actions have equal cost, therefore the shallowest cost is equal to the lowest cost. Okay, so if we wanted to find the shortest path, we would have had to gone an extra depth, and BFS won't let us do that, okay? But if all the path costs here were 1, then we would have found the optimal path. So just make sure that you know that BFS in general is not optimal. But just a quick question out there to people in the chat. In 4-directional search, like this, okay, is BFS going to be optimal for 4 directions? Can you answer that one? I know there's people out there who know the answer to that. Okay, so we got a few yeses. That's correct. So for 4-directional search, it is. What about for 8-directional search? For 8-directional search, is BFS going to be optimal? Yes or no? And why? If you can type why, that would be good as well. Yeah, so BFS for 8 directions would not be optimal. And why is that? Is because the diagonal actions would have a higher cost than the cardinal actions, okay? And since the action costs are not the same, then it's not guaranteed that BFS would find an optimal solution with 8 directions. Now, in some cases, it might. Like, it's not saying that it never finds the optimal path. It's saying that you can't guarantee the optimal path. Alrighty. So BFS is not optimal. What about time complexity? Well, remember, if each state has B children, consider a goal at depth D, then we're going to have B times B times B, and so we have O, big O of B to the power of D nodes generated. So this is an exponential search complexity, so we don't want to do that. That's pretty bad. And the space complexity is also O of B to the D, because we have to store the entire search tree in memory for BFS, and so the space is equal to the number of nodes generated, and this is the number of nodes that we've generated, okay? How about on grids, okay? So if we do BFS with a closed list, meaning that we don't repeat any states, then we can have some really nice properties, okay? So this is applying BFS to a grid can have some really nice properties. So BFS on a grid will have a space complexity equal to the size on a grid, the size of the grid, sorry. meaning that if we don't repeat any states, then we don't have anything to worry about. We're not going to be optimal. So just look at this. Remember from 3200, the yellow nodes or the yellow states here are in the open list and the red states are in the closed list. So if we implement our closed list properly, then we will never repeat any of these red states. That will eventually fill up the entire map, and so we won't have to repeat any of the states in the map. So the time complexity of BFS, and therefore the memory complexity of BFS in a grid, is just going to be equal to the size of the grid. And the benefit that that has for us is that, well, if we can store the grid, right, we've got to have a grid that we can store in memory. That means that our BFS is guaranteed to be able to be stored in memory, right? Because all we're essentially doing is doubling the amount of memory that we're using. Okie doke. So BFS will have a space complexity and time complexity equal to the size of the grid. BFS will find optimal paths for 4 directional movements because all action costs are equal. But BFS may not find optimal paths for octagonal movements because the path costs, which are essentially the distances traveled, are not equal for cardinal movements and octagonal movements, okay? And so what we can do for BFS is we can use 4 directional movement because we're guaranteed to find an optimal path within 4 directional movement, and then we can refine that path later to be a little bit smoother. So last time when we talked about 3/4 of the way through the lecture, we showed how we can use 4 directional movement to do pathfinding in games that didn't have a grid structure, and how we can refine that path later. And so generally what we want to do is, because BFS is a really quick algorithm to implement, it's really cache friendly, and we can have 4 directional movement which guarantees optimal paths within 4 directions, then we can use that 4 directional movement and refine the path later to do pathfinding. And that's what we're going to do with our vector field stuff. Okay, so just remember, again, avoiding repeated states is a huge thing in the search. So if we go back to our graph here, when we were doing our BFS in our general uninformed tree search algorithm, we went from state A to state D, and then we went back to state A. See that? So we went A, D, A, A, B, A. So there was nothing in that version of the algorithm that said, hey, don't go back once you've searched a node, right? Because essentially, if you think about it, if you're trying to find an optimal path somewhere, are you ever going to be walking through the same state twice? Well, obviously not, right? Because if you had to go back, and we're talking about like static environments here, so nothing has changed. But if you ever have to go back to the same state that you've already visited, then that can't be the optimal path, right? So we're going to try and not visit the same state twice. So it's one of the most important search ideas is avoiding repeated states like that. And it's especially important with reversible actions. And reversible actions meaning, for example, in pathfinding, especially in grids, if we can walk up and walk down, then that's a reversible action, meaning that the action of walking up is going to be negated by the action of walking down. So most of our infinite loops, like, you know, we could go A, B, A, B, A, B, A, B, that would be terrible. Most infinite loops or wasted time can be avoided by simply not returning to states we've already visited. So what we can do is we can remember the nodes that we've expanded and simply don't re-expand them, right? And so this can lead to exponential time savings in the number of nodes generated. So the way that we did that in 3200 was by implementing something called a closed list. And the closed list is going to store states that we've already expanded. And it's often implemented as a hash table or a dictionary for efficient lookup, right? We talked about all that last time and how you can use a dictionary or a hash table to do constant time lookup in your closed list, rather than just, say, using a set or using an array and then having a linear time lookup for that. So all we have to do is check to see if a node is in the closed list before we try and expand it. So the open list is the fringe of unexpanded nodes, and that's often implemented as a priority queue. And the closed list is often implemented as a hash table or a lookup, okay? So Our breadth first search using a closed list follows this algorithm. It's the exact same thing as our previous one, except now what we're doing is we're saying if the state of the node is in the closed list, just continue. We are never expanding the children of any node whose state is already in the closed list. Okay, and the same would go for depth first search, but we're not talking about depth first search in this lecture. So what this means, if we look at it, is that yellow here would be the open list, red would be the closed list. So we're going to expand this node, get its children, put the children in the open list, add that node to the closed list. Then for each of those children, we're going to expand to each of their children, add those children to the open list, and add these to the closed list. Okay, and so on and so forth. And that's how we do BFS in a grid. So it's pretty simple. All of you, I'm sure, remembered it. Maybe you have some sort of trauma from assignment 2 from last year's course, but you know, BFS is so prevalent in a lot of algorithms that I wanted to recap it. Okay, so now that we have our refresher on BFS in grids, how do we compute connectivity? To compute connectivity, here's what we do. So as the breadth first search expands, we're going to mark every cell that it touches with some integer, okay? And so that integer is going to be our sector number. And that sector number is going to be stored in a separate grid called our sector map, for example. So everything that a BFS touches must have a path that connects it, right? Because if I got to you with a BFS going up, down, left, and right, then that must mean that a path exists between this cell and the cell that I started at. So any two cells in the final computed grid with the same sector number are connected. So here's what I showed in the last course, is what we're going to do is we're going to implement an algorithm. This algorithm is going to start up here in the top left cell. Now it could start anywhere, right? But it's just easiest to iterate over X and Y in the top left, go left to right, and then go to the next row, go to the next row. So we're going to start here, then we're going to go here, then here, all the way across. And when we finish that row, we're going to come down here and go across, okay? And this iteration is defining the starting point for a breadth first search. All right, so what we do is we're going to start in the top left, and our first number is 0. So 0 means we haven't done anything yet. So we increment the number, and we're going to check first, is this number a 0? If it's not a 0, then it's already been given a sector number, okay? So we're going to set this to a 1, which is essentially just the next number. Then we do a breadth first search outwards from this node, from this cell to its neighboring cells. And we give those the same number. Then from each of these, we're going to do the same breadth first search outwards, giving those the same number, and outwards, until everything that is touched by that breadth first search is given the same number. So what this has done for us, and again, we did all of this in 3200, was now everything that has a 1 in it is connected to everything else that has a 1. So if I'm doing some video game AI logic, and I want to know, hey, can I get from this cell to this cell? Well, I just look up both of the values in the grid, and I say, oh, they have the same number, therefore a path exists between them. Done. It's a really cool data structure that you can do. Now, let's get on with the algorithm. So we started from this spot up here in the top left, so now we're going to move to this spot. However, the algorithm is going to say, if this is not a 0, then skip it. Because if it's not a 0, it's already part of a connected sector, right? So I'm going to keep going along until I get to my next 0. And so I'm going to increment the number and give that one a value of 2. And then I'm going to do the same breadth first search out from this one and fill this one in with 2s. Right? So now anything that has a 2 is connected to anything else that has a 2. Then I continue on with the algorithm until I get here with the 3, and I fill this one out, and then I continue on until I get to this one with the 4. Okay? So at the end, what I have is a connected sector mapping from states to integers. And if two states have the same integer, so for example, can I path find from this one to this one? Well, the integers aren't the same, so no, I can't. And that's a constant time instantaneous lookup once we've done the pre-computation. Okay? So here is the algorithm for this, which is the computing the connectivity. And all this does is it says, okay, I'm going to set up a new sector map. So this is a grid, which is just a 2D array. And it's of size width by height of the map, right? So it's the same size as the map cells. I'm going to give them all an initial value of 0. I'm going to set this sector number, which is the number I'm going to be assigning to each of the cells, to 0. Then for each of the cells in the map, I'm going to loop over the X, I'm going to loop over the Y. And then I make 2 checks. If my sector number is not equal to 0, or my object can't fit at that location in the map, then continue, right? So this was like right here, where I was looking for the next value. Remember? So after I had computed these, this was a 1, skip it. This is a 1, skip it. This is a 1, skip it. I need to find these zeros that haven't been set yet. So that's what that check does. Oh, let me tab through again. This checks for that. So if it can fit, and it is a value of 0, then I'm going to increment the sector number. So that 0 becomes a 1, the 1 becomes a 2, the 2 becomes a 3, and then I'm going to do the cardinal breadth first search outward from that XY location, setting everything to that sector number. And then later on, if I want to check if 2 cells in the grid are connected, then that's really easy. I just check the sector map at X1, Y1 to see if it's the same as X1, X2, Y2, right? So trivial algorithm that you've implemented already if you're in this course. All right. So why did I say all of that? Is because I want to teach you this new algorithm in terms of an algorithm that you already know. So let's talk about vector fields. So in mathematics, a vector field is essentially an assignment of a vector, right? So something with direction and magnitude to each point in space. And so they use it a lot in vector calculus, in differential equations, in physics, in weather simulations. Vector fields are used all over the place. In game programming, a vector will, instead of being assigned to each real value in space, we're going to assign a vector to each grid of a cell. And what that means is that vector is going to denote the desired action or direction of movement from within that cell. Okay, so let's have a look at some examples of vector fields. So vector fields, you've probably seen this sort of thing before, where they're talking about magnetic fields. So magnetic fields are described, and in simulation, they're computed with a vector field calculation, right? So at any point here, you can tell the direction of the magnetic field by its equation in the vector space. In our case, what we're going to do is we are going to be computing a vector field, which, for example, if we wanted to travel to this location, so here's an example usage for this. We're making a video game that's like Diablo or Path of Exile, okay? Where we're going to have hundreds of enemies trying to chase down the player, right? So you've got a bunch of zombies, they're chasing after the player. I gave this example last time. So the last thing that we want to do is have to do something like, for each zombie, run the A-star pathfinding algorithm toward the player. That's just going to be monumentally way too slow, right? So ideally, what we would want is we would have our goal down here. So we have a single goal, which might be the location of the player. And then we're going to make a vector field over the entire environment. And then whenever we want to head toward the player, so if we have a zombie, for example, right here on this tile, right over here, then we calculate a vector field which says in order to get to the player, the zombie should move in this direction. All right? And then what we get from that is something like this. So this is a cool video that I found online where you have a bunch of these particles, and the particles are going to be following a vector field to the mouse location in this application. Okay, so you can see all of these particles, tens of thousands of them, moving in real time toward the player's mouse cursor. And you can be sure that this is not using some sort of A-star pathfinding method. This would have to be done by something like a vector field. All right. So let's look at how that vector field is actually going to be computed. Alrighty. So the first thing that we're going to do is compute something called a distance map. So a distance map, again, here is our goal location, okay? So the goal location here is going to be the goal that we're heading to. Sorry, that was a bit redundant. And then every other cell in the grid is going to denote the breadth first search distance of that cell to the goal cell, right? So remember when we did the sector computation, we breadth first searched outwards, right? So what we're going to do is this cell now is going to have a value of 0, meaning that it is at the goal location. There is 0 distance at the goal location. Except this time, we are calling this thing a distance map. Instead of a computed sectors map, it's going to be a distance map. And the way that we're going to compute this is really, really easy. We start from the goal, we BFS outward, and we assign a value to these cells, which is the current cell's value plus 1. That's it. So here, we breadth first search outwards from the goal. It was its value of 0. So all of the states that are reachable from the goal get a value of 1. And that means if we're doing 4-directional movement, this cell is 1 distance away or 1 movement away from the goal location. Okay? So we do that. For example, this one is going to BFS up here and right here and right here. And then this 1 is going to become a 2. The 1 is going to become a 2. The 2 becomes a 3. And so we're essentially just BFSing outward, and we're marking each cell on the grid with the depth of the breadth first search that reached that the first time. Okay? So that's called a distance map. Second, what we're going to do is we're going to take that distance map, and then all we need to do to traverse toward the goal location, whereas this would have been a complex pathfinding algorithm in a past lecture, all we need to do, so let's say we're at this location, right? We just look to go toward an adjacent cell which has the lowest value, okay? This was the worst example for me to pick because they all have the same value. So let me discard that and I'll come back in. So let me choose, I'll choose this one over here, okay? So we look at its adjacent cells. Should we go up? Well, my current distance from the goal is 9, right? Where do I want to go in order to head toward the goal? Well, I certainly don't want to go towards a cell that has a distance of 10 because that's getting me further away from the goal, right? I want to go toward a distance of 8, which is an up, down, left, right, or in this example, they're allowing diagonal movement. So I'm looking at the cells around me, and it says, oh, look, this adjacent cell has a value of 7, so I want to head toward that cell. Okay? So all we need to do to find the shortest path to our goal is traverse from the current cell to the adjacent cell with the smallest value. Okay, so what does that end up looking like? Well, this is sort of the under the hood, behind the scenes of what happens in that simulation that I showed you, right? So here's the vector field, and all that's happening behind the scenes is that when you want to update the position of these particles, you just move the particle in accordance with the cell, or the vector field direction, okay? And then, as you can see, these particles have a bit of smooth movement to them, and so that smooth movement has been implemented by a steering behavior. So in assignment 2, we are essentially going to be implementing what you see here, okay? We're going to be doing all of this. So you're going to be given a grid, and we'll talk about this in the next class, and you're going to be able to edit that grid, you're going to be able to move obstacles around, and your pathfinding algorithm is going to be computing a distance map, then a vector field, and then you're going to have a bunch of particles on the map which move around in accordance to the vector field, okay? So that's what a vector field is, and that's how it's going to be used. So vector fields for games, sometimes they're called flow fields, they're called influence maps, they're called vector maps. It's a very efficient structure for pathfinding in the case of many agents to a single goal, Okay, so if you have a bunch of agents and a single goal, I think you should probably use vector fields. It's a very good way to compute that. So any case where we have multiple NPCs that need to go to a single location, consider using a vector field for that. It can be used to accomplish a number of tasks, not just pathfinding, but pathfinding is the one that we're going to be talking about in this course. So let's look in more detail again. I know that, you're probably smart enough to go out and implement this, but I want to have more detailed notes for you. So before we compute the vector field, we need to compute that distance map, right? So that's that grid that we showed you. Each cell of that grid will store the 4-directional shortest path distance to a single goal cell. So in practice, we are going to need one distance map per pathfinding destination or per goal. And we can cache those maps if necessary. So essentially, we're going to need, if this is the goal down here, we will need to have a distance map that represents that goal. And then if we move our goal, if the player moves, we're going to have to recalculate that distance map. So here's how we calculate the distance map. We start with our goal location and we give it a 0. And then for each new depth of the BFS, we increment by 1 and we mark that cell with that value. Okay? So these are the 2s, these are the 3s, etc., etc. And what we get at the end is this distance map. Okay, so the distance map is going to be 0 at the goal location, and it's going to mark the depth of the breadth first search at each cell when it was touched. So over here, we do not have any values in here for the distance map, and if we don't have a value that's set, well, that means it cannot be reached from the goal location. Okay, and again, if we want to figure out which direction we should head in, for example, from this 15, then we're going to look at the adjacent cells. So we're going to be doing up, down, left, and right for our assignment. And we see, okay, there's a 16 here, and 2 14s. So it just so happens in this case that we could head right or down in order to get to the goal in the fastest way possible. Cool. So the distance map is computed via BFS in a similar way to the connected sectors, right? But instead of marking each cell with the same value, we're going to give it a value of the parent plus 1. And we're going to give each distance map cell an initial value of -1. And that means once we're finished computing the distance map, any cell that has a value of -1 is not reachable from the goal, okay? So just watch this. If I go back here, under the hood, each cell is going to start with a value of -1. Okay, so all these green ones are going to have a value of -1, and then everything is at the beginning. And then as we BFS outwards, if anything at the end still has a value of -1, then it can't be reached from the goal. So we can use that as a sort of connected sector check as well, where anything with -1 can never reach the goal. Once we have the distance map, now we have to do the vector field computation. And so from the distance map, it's very easy to construct this vector field. Each cell, all it does is it gets assigned a vector or a set of vectors pointing to the lowest neighbors. And so sometimes we may have an optional example. We're not going to do this in the assignment, but if a cell points to both left and up, instead of having, one pointing left and one pointing up, we're going to just say one up left. That's it. So again, computing a vector field is pretty simple. Step 1, form the distance map. Step 2, point to the lowest adjacent value. Step 3, profit, right? Very, very simple. You should all be able to do this with no problem on the assignment. All right. So that is that algorithm. The last 4 slides came from this excellent blog article about how to implement this, and you're completely, what's the word that I'm looking for? You're free to go look up that and to help you with the assignment, but I think that you're all capable of implementing this for the assignment. So now that you know how to do it, the really cool thing I think personally about assignment 2 is I want you to spend 90% of your time in assignment 2 trying to make your algorithm run as fast as the solution. Okay? So I know that, you may not get to be as fast, but I've spent a ton of time optimizing my assignment 2 solution to the point where if anyone beats it, I really want to talk to you about what you did, because I think I've reached the limit of how far that I can push it. And it's to the point where when I naively implemented just like a bunch of for loops and integer storage and all that kind of thing, my current solution is at least 100 times faster than that. So keep in mind that just because, your initial solution may not be as fast, but I want you to really dig down and try and be as fast as possible with assignment 2. Okay? And again, the top 8 fastest times in the class are going to get something special. So really try for that. A lot of people in the last class really did try for the fastest times, and they found they learned more from that than almost anything else that they took away from the assignment. So I'm going to give you some performance notes here, some of the sort of high-level abstract theoretical ways that you can improve your performance over implementing like a naive breadth first search like in 3200. So actually implementing BFS in an iterative way using a queue is going to result in poor performance, right? The reason for that is that a vector implementation of a queue needs to left shift all of the elements to pop from the front, which can be very slow performance in practice. What do I mean by this? Okay, well, let's have a look. Here's a queue. This is a very poorly drawn queue. So let me put some cells in here. Most queue data structures, especially if you're using like a vector, because a vector is basically a queue, vectors are very cache friendly. So we want to use them, right? But in a queue data structure, I'm going to be pushing things into this queue, right? Queue is first in, first out, meaning that when I want to take something out of the queue, I'm taking it from the front of the queue. However, in most programming languages, and anywhere that we're going to be using arrays like this, if I delete something from the front of a vector, then the way it implements that is by left shifting every element in the vector. That's the way this is actually implemented, okay? If I want to delete any element from this queue, then I'm going to have to move everything in front of it to the left until it reaches where I deleted from. And so that very simple operation of deleting or popping from a queue is actually a linear time operation in practice, okay? Now, you may say, yeah, but I don't need to use a vector for that, right? I could use some like pointer-based queue or something like that. Well, the problem with doing that is that you're no longer cache coherent. And so your bottleneck then may be cache misses instead of this linear time operation, right? So it's actually quite complicated in practice to optimize this perfectly. So let me just discard these annotations and come back. So performing lookup in a closed list can also be very slow if implemented poorly. So I'm going to give you 2 optimizations that you can start with, all right? However, please keep in mind that whenever you're doing any optimizations, the vast majority of the marks for the assignment are just going to be in getting the thing working, right? So please do not implement any of these optimizations until you have everything working correctly. So the functionality is more important than the optimization, but once you get it up and running, then you can start implementing these optimizations. And I highly recommend that once you get it all working, please start, trying to do some optimizations. So here's the first optimization, and this is how you avoid a queue and the deletion from a queue when you're doing a breadth first search. So what we're going to do is instead of using a proper queue that's going to delete things from the front, we're just going to use a vector. And so if we want to insert into the queue, you're going to push the state into the back of the vector. That's normal, right? So pushing onto a queue means inserting on the back. However, instead of actually removing from the front of the queue, what we're going to do is we're going to have a pointer or an index that's pointing to the theoretical front of the queue. And instead of deleting, we're just going to move that pointer forward. And I have an example of this. So instead of checking if the queue is empty, instead we're going to check if the pointer is pointing to the end of the queue or not. Okay, so let's look at a visual example of this. So here we have a vector which is currently has one thing in it. Okay, so it has one thing in it, and we are going to push a few things into it. So what we're going to do is we are going to push a bunch of things into that queue, and then we are going to want to delete the first element of that queue. But instead of actually, in the implementation side of things, looking at the queue, removing this element, and shifting everything to the left, we are simply going to increment a pointer to now say, okay, I'm no longer concerned, both my things are red. I'm no longer concerned with the thing I deleted. So instead of starting at 0 when I iterate through this queue, now I'm going to start at 1 when I iterate through that queue. See how that works? So I have 4 things that are still in the array, but I'm only looking at the final 3 things of that array. Now, let's say I push some more things and pop another thing, right? Instead of actually removing this data from the queue, which is a linear time operation, I'm just going to be moving that pointer to the right by 1, okay? Now I'm at this point, and let's say I haven't added anything new to the queue, but all I'm going to do is going to increment the index to the right. So if I want to remove this element from the queue, all I have to do is increment to the right. So let's say I keep removing things from the queue, right? I keep removing things and removing things. How do I tell when the queue is empty? Well, I tell when the queue is empty when the beginning pointer is equal to the final pointer, okay? So what we're doing here is we're trading memory for speed, because our BFS queue is never going to be removing, like we're never actually removing the memory. We're just sort of forgetting that it's there, okay? But the real hard operation in a queue is the delete operation. And what we've done is we've actually removed that linear time operation. So we're trading memory, we're giving more memory, but we're getting a lot more speed. And in this case, we know for our BFS, it's going to be at most the size of the grid. So we are guaranteed to know that our BFS queue, this structure, can fit in memory. It's not going to get exponentially large or anything like that, right? So in this case, we can implement this and we can get the best of both worlds. We know it's going to fit in memory, and we know that we're going to have a very fast popping type operation. So I see a bunch of people in the chat asking some questions. Someone said there's probably a library that does that. Yes, but this is a university course. We're not some chumps using libraries, right? That's for front-end web developers. We are game AI programmers, and we are implementing it all from scratch because that's what real programmers do, right? So this is an academic course meant to teach you the theory and get you to implement it yourself. So it doesn't matter if something else exists. There's something else that exists for everything, right? We are in the business of speed, and speed means doing it yourself. All right. So that is the optimization for implementing a very, very fast queue data structure. And it's theoretically impossible to get faster than this, okay? If you know that your queue is going to fit in memory. How about the breadth first search? We talked about the closed list, right? So this closed list is a data structure. And so the data structure of the closed list, if you let me draw poorly again, at some point is going to look something like this. This closed list, if you implement it as a set or as a vector or whatever, at some point you're going to have like a bunch of cell locations in this closed list, right? So you're going to have a bunch of cell locations, and then at some point, you're going to say, is this cell inside the closed list? So yeah, you could use the vector built-in contains or standard find or whatever, right? So you could go, is 1, 2 equal to 7, 6? No. Go to the next one. Is 4, 8 equal to 7, 6? No. Go to the next one. Is 10, 9? Linear time operations suck, okay? And we want to avoid them if at all costs. All right. The cool thing about this algorithm is that we can use the distance map's initial values as a constant time closed list query instead of using a dataset. So, how does that work? Initially, we are going to assign the distance map cell values of something unique. So when we start the distance map calculation, everything is going to get a value of -1. So that's unique. Distance can never be negative, right? So we're going to set them all to -1 in order to mark this has not yet been computed. Okay. And the goal is going to get a value of 0. So that means any state which has not yet been visited has a value of -1. So to query if a state has already been seen by the distance map's BFS, you don't need a separate closed list. All you need to do is check to see if the distance map is not -1. So if you look up the distance map's value, if it's -1, it's not in the closed list. And if it is -1, it is in the closed list, right? So if you can't do that for whatever computation you're using, then you could use a separate Boolean grid. However, in this case, you can definitely do this. And here's what it's going to look like at some point, right? You're going to start from this goal, and you're going to BFS outwards. And at some point, your grid is going to look like this. You haven't finished the BFS yet, right? And you want to say, is this cell in the closed list? All you have to do is check to see if it's -1. If it is -1, it's not in the closed list. If it's 2, it is in the closed list, right? So that means it has been visited before. Or if you wanted to, you could have a secondary Boolean closed list which has trues and falses, right? Okay, so that's another optimization which is going to save you a ton of time, running time in assignment 2. What I would recommend is get assignment 2 working, run it, do the timing test. I have tools built into it that have specific timing tests. Like you can just hit a button and you get a number, and that's your score. So see what your score is in your initial implementation, and then implement these optimizations, and then see what your score is. And to me, there's something so beautiful about that side of optimizations. Is like it's one of the very few times in life where you can just like prove that something is better, right? Like there's no opinion anymore. It's like, this is better than that because this number is lower. And I love computers for stuff like that. I can show you that this thing is objectively better because it's just faster, right? And that like consumes me when I do my research and my algorithms, is trying to make things as fast as possible. So I highly recommend, come to me on Discord, talk to me about it, post your fastest times in the Discord as you're optimizing things. I want to see that sort of, like, it's not competitive in a negative way. It's competitive in an uplifting way to be able to show people what is possible, right? And to get them to strive to be a better programmer or a better AI programmer at the very least, right? Is to get things correct solutions first, but fast solutions a close second, okay? All right. So the last thing I want to end on is the notion of influence maps. So influence maps are very closely related to the topic of vector fields. Influence maps typically incorporate other logic than just simple distance to goal, okay? And the reason for this is because sometimes in your games, you're going to want your AIs to behave in some way that is not necessarily optimal distance movement, right? So maybe, for example, there's an explosive barrel, and you want your pathfinding to still have like a decent path, but maybe avoid getting too close to the explosive barrel, right? So the game design functionality is going to have some influence over the movement of the creatures in the game, right? So they can be used when it may be difficult to construct an objective function for other algorithms. So for example, if you wanted to avoid that explosive barrel, how would you code your heuristic or your F cost in an A star search algorithm, right? You'd have to have some weird like hidden values. Like it'd be kind of strange to be able to do that, right? To take that F cost for your A star algorithm and incorporate explosive barrels somehow. But with influence maps, it turns out that can actually be pretty easy. So some examples of influence could include keeping distance from obstacles or enemies. That's kind of the explosive barrel thing. Avoid attack damage from enemies. So for example, if you have a pathfinding system in an RTS game and you send your units at the player, but the player has some towers or some cannons or something like that, some bunkers, you may want your pathfinding, still go towards the base, but maybe steer away from those things too. And influence maps could help you do that. Or any combination of things. So here's sort of the idea of an influence map, and it's related to the idea of a distance map or a vector field, okay? So let's say here that we have a start and we have a goal, and the very simplest possible influence map would just say, don't walk on this tile, right? So if we have an enemy on this tile, it would just say, okay, I can't walk through that enemy, right? So I can't walk through that enemy. So the influence map would just be something that says avoid this tile, but that's not really interesting. Let's move on to the next one. Let's say we're in a boat, okay? And we are in a boat and we are trying to avoid going into shallow water. And so we've got shallow water around this island and we want to avoid that if at all possible. So what are we going to do? Well, one idea would be to give a repulsive influence to the areas on the map that we want to avoid, okay? So what this means, essentially, is that whenever we do our distance map, we're going to add that value of 10 to the distance map. So then we calculate our distance map for our vector field, and the influence is essentially saying, I would rather go an extra 10 distance than walk this close to the shore. Right? And so it's tied in with the idea of a vector field, and it's adding influence to areas that we would want to avoid. And the cool thing about influence maps is that we can add different influence maps together. We can combine them. So let's say we had this influence map of avoiding the shoreline, but we also want an influence map of avoiding an enemy. Right? So we want to avoid this enemy, so we give a huge avoidance value to the enemy and the surrounding tiles around the enemy. Maybe this is a turret that can like one-shot us or something. And then when we compute the distance map, we really want to avoid this enemy. And like the only reason we would ever walk toward this enemy is if there's multiple other enemies at another location. Okay? So just like an idea of a distance map. This is an example of a repulsive influence map that is helping guide the pathfinding of this blue unit. So the blue unit is trying to find a safe spot that is away from these red enemy units, and that's being done using an influence map. Here we have sort of attackers versus defenders, and so the influence map could be used to like push away these attackers. So the blue ones are defenders. The blue ones are attracted to the attackers because they're trying to defend. The red ones are attracted to this base location because they're trying to attack it. And so you have this like cool interplay where you're using influence maps to decide the behavior of enemies without coming up with like a bunch of strange or convoluted values for your A star costing. Okay, so we're not going to be implementing influence maps in this class, but I just wanted to show you that it's sort of the next step on top of vector fields. You could start inputting this influence and stuff. So in the next class, we're going to be talking about assignment 2. And just to give you a sneak peek at assignment 2, as a teaser, I'm going to run it here again. So assignment 2 is going to look like this. And in assignment 2, we're going to be doing several things. Here, the yellow location on this grid is my goal location. So I can left click to set the goal location. I can take these obstacles and move or resize the obstacles. And as I'm doing that, I am updating our little navigation mesh grid here. Okay. So I've got this navigation mesh grid, which is being updated in real time as I drag obstacles around. I'm going to be, what is my key here? 1 second. Here we go. So here you can see this is, as I'm dragging the goal around, I am computing a distance map in real time. And then if I hit the button again, I see the vector field being updated in real time. And this is a vector field on 4 directions. So this cell right here would mean, okay, I can move to the right or I can move down to get to the goal as fast as possible. And then on top of that, we are implementing a particle system. And the particle system is going to be following the vector field with some steering behavior built on top of it to make it look nice, okay? So this is what that's going to look like. And you can see that, like, if I drag this over and block this off, then the particles follow the vector field around. And you can put lots of particles here, and it's very, very fast. So here, for example, I am doing the pathfinding for 262,000 units at 50 frames per second. So the pathfinding and the path following for 262,000 units at 50 FPS. Okay? So I'd like you to try and get to that level in your assignment as well. All right, so that's just a sneak peek at assignment 2 and why all of this matters. So let's see, let's go back to our schedule. So remember that there is a quiz that is going to be released right now if you're watching live, or if you're watching on YouTube, it has already been released, and you have until Sunday evening to do that, and it covers the last 2 lectures. And on Tuesday, we are going to be covering assignment 2, and I think it's going to be a really fun assignment, so please stay tuned for that one. And as a reminder, if you are not in the course, you will not be given the assignment files for any reason, even if you are the Pope. Okay, and I have had a lot of people emailing me recently asking me for assignments for all sorts of like various COVID-related reasons. Nope, you got to be a registered student in the course to get the assignments. Sorry. All right, well, I'll see you next time for the assignment. And remember that assignment 1 is due on Tuesday as well. So get that finished up. See you next time.